integrated project requires us to build one new combined gas steam power station in Lumut Naval Base to meet its economic and population growth with aim to produce a total of 500 megawatts electricity. Our group was assigned to take water as the cooling medium. This combination cycle plan of Brayton cycle, which is for gas turbine, and Rankine cycle for steam turbine, work by capturing waste heat from the gas turbine to produce steam, and consequently, the steam is used in a steam turbine to produce additional electrical output with higher efficiency. The computation starts with the Rankine cycle that employs water as the working fluid to produce the electrical power. The Rankine cycle will undergo 4 processes, which is for process 1 to 2. Superheated vapor enters the turbine where isentropic expansion takes place, and then the work produced as the shaft connected to the electric generator rotates. There will be a pressure drop and temperature drop of the steam before entering the condenser. For process 2 to 3, the steam, which now usually appears as saturated liquid vapor mixture high quality, condensed at a constant pressure to become a saturated liquid, then leaves the condenser to enter the pump. For process 3 to 4, water is saturated liquid state now, so it enters the pump and compresses isentropically. As specific volume of water decreases during isentropic compression, the T will increase. For process 4 to 1, water in compressed liquid state that enters the boiler and receives heat at constant pressure. Water will leave as superheated vapor into the turbine bag, which is completing the cycle. Moving on to the Brayton cycle, which consists of 2 isobaric processes and 2 isentropic processes in its ideal form. The 2 isobaric processes include the combustor system of the gas turbine and the gas side of the HRSG. The 2 isentropic processes involve the compression by the compressor and expansion in the turbine. The processes that will take place in the Brayton cycle is from process 1 to 2, which is isentropic compression in compressor, process 2 to 3, where there will be constant pressure heat addition into the heat exchanger, process 3 to 4, isentropic expansion in turbine, and process 4 to 1, which is constant pressure heat rejection in heat exchanger.
Moving to the calculation and assumption part, the calculation is done both on the Rankine cycle and Brayton cycle. A assumption is made for the Rankine cycle to complete the calculation, as shown in this slide. Our design is evaluated by performing energy balance at each device. The first device is turbine. As we mentioned in the assumption, inlet temperature is 1700 degrees C and inlet pressure is 30 megapascal. We determine the fluid property by referring to the table A6 at 700 degrees C. Next, as we know, the process undergo in the turbine is isentropic process in which the entropy S4 is equal to S3. The properties is determined using the entropy and pressure by referring to the table A5. As the entropy in stream 4 is situated between saturated liquid and saturated vapor entropy, stream 4 is clearly in saturated liquid and vapor mixture. So, to get the total specific volume and enthalpy, we need to determine the mixture quality first. The mixture quality is then used to determine the specific volume and enthalpy in stream 4. And then we calculated the enthalpy difference. And then the enthalpy difference is used to determine the mass flow rate needed by using the assumption of the 50 megawatt of the power in the output of the turbine. Then the mass flow rate needed is multiplied by 4 because we have 4 turbines in our design, and the work output of 4 turbines is 200 megawatts. The next device is condenser. Condenser is operated under isobaric process, meaning both pressure in stream 1 and stream 4 is the same. The temperature assumption is 50 degrees Celsius because it has to be greater than 37 degrees Celsius, which is the surrounding temperature. The stream 1 property is determined using the table F4 at 50 degrees Celsius. After getting all the property in the stream 1 and 4, the heat transfer out of the condenser can be calculated by multiplying the mass flow rate and the enthalpy difference. The heat transfer out of the condenser is 246,993 kilowatt. After that, we also have pump in our cycle. Property in stream 1 is already been determined. For stream 2, entropy in stream 2 is same with stream 1, while the pressure in stream 2 same with stream 3, which is 30 megapascal. Use this entropy and pressure to list out all the properties in stream 2 according to the table A7. Work into the pump then is calculated using the mass flow rate and the difference in enthalpy. The boilers, property in stream 2 and 4 is already found in previous calculation. And so, the heat transfer into the boiler can be calculated, which is 443,099 kilowatt. So, to find the network output of Rankine cycle, work produced by the turbine is subtracted with the work required by the pump. Steam generated can also be calculated, with mass flow rate multiplied by the specific volume. Now we move to the second cycle, which is Brayton cycle. A few assumptions is made for the calculation as shown in this slide. Now, to begin the calculation, process 1 and 2 is isentropic. Relative pressure is determined by using the formula PR2 over PR1 and equal to P2 over P1. By interpolation, enthalpy and temperature is taken according to the relative pressure we calculated. Same formula is used in process 3 to 4 to find the pressure 4. By interpolation then, enthalpy and temperature is taken according to the relative pressure we calculated. For heat exchanger, value of heat transfer out is extracted for the Rankine cycle calculation. After then, this equation is solved so that the total mass flow rate for two turbines can be calculated. Now, use M multiplied by the difference between H3 and H4 and we get the total work for the two turbines. Use the same formula to also find the work required by the compressor. Work net total is calculated from the summation of work turbine out for gas and steam and heat energy that leak from the condenser. To find the mass coal needed, the work net out total is divided by the heating value of the coal that we assume. Lastly, for the whole combined cycle, the overall actual work produced is 561.48 MW. For thermal efficiency, use the formula 1 minus Q out over Q in. The thermal efficiency we got in percent is 75.41. Then, we determine the back work ratio using this formula and the back work ratio for our combined cycle is 0.25.
In conclusion, this power cycle was produced with the combination of Rankine cycle and Brayton cycle. The combined power cycle was designed with the setup of devices consists of 4 steam turbines, 2 gas turbines, each set of generator for both cycle, compressor, heat exchanger, and condenser, with well-insulated pipelines to prevent the heat loss to the surrounding. From the design, the value of thermal efficiency for the combined cycle that were calculated is 75% and backward ratio is 0.25. The power plants require 29.77 kg mass of coal per second and will generate 1.727 meter cube per second of steam. In regards, with all the results obtained, electricity generated is enough to supply output power needed to Lumut Naval Base.
The recommendation to increase the overall efficiency of the combined cycle power plant is the pace of the energy production should be near enough and strategic to the population in order to minimize the heat loss. This is because when the heat loss is reduced, the network output will increase, that lead to the thermal efficiency of the whole system will be increased. And the second one is lowering the condenser pressure in Rankine cycle will causes the steam condense at lower pressure. This will lead to the expansion through the turbine, which will increase the net work done by the turbine.